Real-world scalable entity resolution. I am Nick Bates-House, Chief Architect of Tamr, and in this 5-part video series, I'm describing the challenges of entity resolution at scale in the real world and what Tamr has done to address those challenges. In part 1, I talked about why it is hard. We unpacked entity resolution at scale and a bunch of the challenges hiding inside, and gave some measures of success. In particular, we showed that we're able to perform entity resolution on 500 million records representing the entire population of the United States. We're able to do that in under 3 hours and under $300 on commodity scale-out compute infrastructure. What's more, we're able to process a 1% delta, that is 5 million records representing adds, deletes, and changes to that 500 million record baseline. We're able to do that quickly and with stable IDs. In part 2, I'll talk about how we make the easy part cheap. We'll start with a definition of what is easy and what is cheap. We'll cover the data processing workflow, and then again, give some measures of success. So what is easy and what is cheap? Easy here means easy for a human to decide. Entity resolution at scale is rife with easy cases, obvious matches, and obvious non-matches. Here you can see one example of 2 records that have the same values in all of the identifying columns. They have the same name, address, city, state, and zip code. They are obvious matches. They are obviously referring to the same entity. Conversely, you can also see an obvious non-match, 2 records that have different names, different addresses, different cities, different states, and different zip codes. These obviously refer to different entities. That is easy for a human to decide. Our goal is to also make it cheap for a computer to decide. Which begs the question, what is cheap? We'll start with an understanding of what is not cheap. The naive approach to entity resolution is to compare every record to every other record. For our 500 million record example, that's 250 quadrillion comparisons. It also involves petabytes of intermediate data. Nobody does it this way. What is a cheap way of dealing with obvious non-matches? We create blocks of records that are possible matches. With k records in each block, we now need to perform only k-squared comparisons within the block to process the possible matches. But more importantly, when 2 records do not share a block, there is no possible match and we do no work to compare those records. Having records that are obvious non-matches, not share any blocks, eliminates the vast majority of that n-squared space. To handle obvious matches, we can efficiently find groups of functionally identical records. We'll unpack what we mean by functionally identical, but you can think about it as records that have the same values for all those identifying columns. We're going to replace each group of records with a single representative record. This dramatically reduces the k, the number of records in each block, which leaves effectively order of n work to do rather than n squared. With that understanding of what is easy and what is cheap, we can talk about our data processing workflow. This is our end-to-end data processing workflow. In this part, we're only going to cover the first 4 steps, which is dealing with the easy part. Step 1 is pre-grouping. This is dealing with obvious matches. Our goal is to group together records that have the same values in identifying columns and create a representative record using some clever aggregation on the other columns. This is almost, but not quite, a SQL group by. Groups are identified by specifying the columns in the grouping key, and we group the records by value. And this differs from a SQL group by in that we do not group by empty values. All records with empty values are left as singletons. Interestingly, we do not group by features. In machine learning, we process the values in the data to make them more palatable to machine learning. We don't do that here because it's unnecessary. Doing it, if we were to group by features, we would end up doing feature extraction twice, once on the source records and once on the representative records. We omit that first one, performing feature extraction on source records, which lets us do pre-grouping by value rather than feature. The second thing to note is that pre-grouping has a single clause. There's a single set of columns in the grouping key. We found it unnecessary to support multiple clauses in the grouping key because the entire data set represents the same type of entity. These are all B2C customers, or all B2B suppliers. And being that they are all the same type of entity, they all have the same identifying columns, and we can have a simple grouping key. This keeps pre-grouping simple and efficient. Once we have identified groups of records to assemble together that are functionally identical, we can perform aggregation. And we perform aggregation only on the columns that are necessary for the machine learning later in the workflow. There are two really meaningful forms of aggregation that we use. For strings, we're collecting a stable subset. And that stable subset, we're using the min-hash approximation of Jacquard. And you can, on the back of the napkin, figure out why this min-hash approximation is going to converge towards the common values across all of the records in the group. For numeric values, we're using the mean of the values on the records in the group. And again, law of large numbers and regression towards the mean, or the mean of the entire population, then tells us that this is the correct aggregation to use for identifying numeric columns. And then we also maintain a mapping from the representative records back to the source records that form those groups. Once we have done pre-grouping and we have formed groups and representative records, we're ready to perform feature extraction. Feature extraction converts sets of values for use by machine learning. Keep in mind, in pre-grouping, one of the techniques we use to create values for machine learning is that stable subset. So we have a set of values on each representative record rather than a single value for a column. To convert these sets of values for use of machine learning, we're just looking at identifiers, location information, contacts, etc. We don't need a lot of features. There are techniques out there for doing deep feature engineering where you can apply a machine learning workflow to identify the perfect set or the optimal set of features for your data for the machine learning to provide the most accurate results. What we find is that this is unnecessary. Not only is it unnecessary, it actually missets data consumer expectations. If you deliver data with perfect output that is fragile in the sense that the next time you get a data update or onboard a new data source, the quality of your model is going to go down or your time to delivery is going to go up. Customers' expectations have been set to have perfect output in a timely manner, and they become frustrated that the update cycle is slow or the data quality has dropped. Much better is to set their expectations that they can provide feedback on the data and get any errors or issues that they identify addressed quickly to maintain high quality over time while still keeping a short time to delivery when the data is changed or updated. So a small set of features, not heavily engineered, just used to perform the machine learning on those identifying columns. So what features do we use? How are values converted for use by machine learning? We really have just a few techniques that we find are broadly applicable. Text is tokenized and lightly lemmatized. And by lightly lemmatized, I mean that we standardize case and we standardize diacritics. We're not doing linguistic lemmatization like stemming or decompounding or anything like that. What we find is that for the type of short text that appears in titles and names, linguistic lemmatization is unnecessary and does not provide a significant boost to recall. Conversely, it's also expensive. Instead, to address things like spelling or non-standardized orthography, we can use bigram. And bigram splits the tokens up into pairs of letters. And then we hash the values to 64-bit longs. This is because modern commodity hardware is best at streaming 64-bit values, and we want to play well with modern compute memory hierarchy. The last thing that we do for text is we compute the IDF, the inverse document frequency, on the entire corpus, and we use that later in IDF weighted cosine similarity. For numbers and geospatial features, we just pre-process the features so that all the values are 64 bits, again, to play well with that memory hierarchy and streaming of 64-bit values. So what is blocking? Blocking quantizes features into overlapping blocks. Each record is going to be assigned to multiple blocks, call it B blocks, and we would like each record to be assigned to some number fewer than 100 blocks. Conversely, each block is assigned some number K of records. These are the records that we're going to compare to each other. These are the possible matches, and we would like the maximum number of records in a given block to be much less than 1,000. 10 is ideal. We're going to compare records within a block. This gets us that order of K squared comparisons, and if K is small, order of 10, that's effectively a constant, and that's what gets us to the order of N number of comparisons to do entity resolution. This implicitly prunes all pairs of records that do not share a block. This is that enormous pruning power of blocking and is extremely useful. The other thing to note is that block assignment, that is computing all of the blocks on each record, is linear in the number of records. So how are features quantized? For strings, we know that when it comes time to compare two strings, we're going to use IDF-weighted cosine similarity. So a block is the subset of tokens from that value that can meet that similarity threshold, given their inverse document frequency, given their weights. We use an A-star search to go and find the possible subsets where that subset, another record with that subset can meet the similarity threshold, and we record all the viable subsets. Those are the blocks for a string feature. For a numeric feature, we know that when we perform similarity, we're going to use numeric difference, and we're given a threshold for similarity. Values need to be within a threshold to be meaningfully comparable. So we create blocks that are twice the width of that threshold and overlapping by that threshold, and assign blocks the value divided by 2 tau, and of that, the value plus tau over 2 tau, those overlapping blocks are assigned to the record. For geospatial features, we do the same numeric quantization, the same numeric blocking, but we do it in 3 dimensions. So essentially, we assign overlapping voxels to geospatial points. All of these blocks are hashed to 64-bit integers, again, to play well with the memory hierarchy, and they're stored in such a way to facilitate retrieval by block. This will be important later. Blocking is specified using a blocking model. The model has one or more clauses. Each clause has one or more terms. Each term describes a feature and a similarity threshold. Here you can see, for example, I've got a name feature with a similarity threshold for IDF-weighted cosine in conjunction with a phone number. Those two together form a clause, and what we can do is create clause-wise blocks. I take all the blocks for the name feature and all of the blocks for the phone number feature, take the cross and hash those together. Those become the blocks for that record for that clause. So we have clause-wise blocks determined by this set of terms grouped into clauses that describe conditions under which two records are potentially meaningfully comparable. Once we have identified blocks, we've assigned blocks to records, we have stored those, we now process blockwise. This is why it's important to be able to retrieve the data in block order. We're now going to retrieve blockwise and process each block to identify first all pairs in the block, but now keep in mind the boundaries, the width of those blocks is greater than what is strictly specified in the blocking model. For example, numeric blocking, we have 2 tau. Blocks are width 2 tau, but the threshold is only 1 tau. So we're going to filter out any pairs that don't strictly meet the blocking terms, the terms in the blocking clause. Note that this is sub-block parallelizable, so we don't really care about a lot of skew in the size of blocks. We can still subdivide and process individual large blocks across multiple nodes in our scale-out compute infrastructure. So we compare quite a few pairs, or we consider quite a few pairs but then we only generate k times n pairs. And this makes that comparison part of the entity resolution problem order of n, the number of records, rather than n squared. This is a pretty phenomenal reduction in the amount of work that we need to do in order to perform entity resolution at scale. That's the easy part of the data processing workflow. We did pre-grouping, feature extraction, blocking, and pair generation. How do we know we've been successful? Let's talk about some measures of success. In our example of performing entity resolution on the entire population of the United States, we started with 500 million records. With blocking, naively, that will produce 250 quintillion pairs. With blocking, we're able to reduce that to 5 billion pairs. Still large, but practical. You can actually process that in a day rather than 100 million years. With the addition of pre-grouping, we reduce the number of pairs to under 1 million. Not 1 billion, not 100 million, not 10 million, but under 1 million. Not only does this reduce the amount of work that the machine learning needs to perform dramatically, it also allows us to focus our machine learning on the interesting cases. We don't need to invest a lot of training in ensuring that the machine learning gets the easy cases right. We can have it just focus on those hard cases on the decision boundary. This is the end of part 2, how to make the easy part cheap. We covered pre-grouping, feature extraction, blocking, and pair generation, collectively the easy part, and provided a measure of success in which we are able to reduce the number of comparisons we need to do on those 500 million records to under 1 million pairs. I'm Nick Bates-House, Chief Architect at Tamr. Please join me for the next part in which we talk about how to make the hard part scale.